We're continuing our discussion on data engineering, preparing our data for AI algorithms. And in our previous video, we looked at how we separate into training and testing data if we're doing supervised learning, that we standardize or normalize if we have predictor variables that have different ranges. And we talked about that we need to have a variable we can use for the label if we're doing a supervised machine learning method like classification or neural networks. Something that you know what group it falls into, so you can then train your algorithm to identify those groups or classes. So we talked about labeling, using existing labels or how you can label by hand. And then we talked about how you can take particular variables and encode them so that you have them in a form as a label that is usable. So for example, you could take your 5-star review and you separate them into the positive and the negative. So we're encoding or manipulating our variables so that it goes from being 5 different options to being binary, positive or negative. So we can do one-hot encoding where we take a variable like here species where there are 3 different types and we turn them into, I'm just going to move my face. So we turn them into 3 variables like you see there where each variable is a yes or no. So in this particular video, we're going to talk about imbalanced data. What do you do if your labels are predominantly one classification or one label? So for example, let me just show you this data set here. This data set here looks at banking services, and they're trying to predict whether or not someone is going to buy a GIC. And when it comes to the data set, 86% of those in the data set said no. So we have this majority class, so the predominant label is no, and then we have our minority class, the other label, which appears a way less frequency, and it is the yes. So the problem this creates is that the model is biased to the majority class. So a terrible model, a model that had no predictor variables that were even related to this data set at all, would still be highly accurate because the model would just say everyone is a no, and it would be 86% accurate. So this becomes problematic because if you are the business that is selling these banking services, you need to know who is actually going to buy these GICs. So who do we target? Who do we spend our effort on to get sales? It doesn't help us at all as an organization to say, let's just assume no one's going to buy our stuff. In which case, why do we exist? So we need to create a classification model or a neural network that allows us to say, okay, can we identify whether or not someone is going to buy our product? But we need it to be that we can actually figure out the pattern in terms of who the yeses are, even though our data set is mostly no's. Okay, so our variable, what we're trying to predict, our response variable or our dependent variable is mostly one label, but we really need to be able to find the minority class and what's happening with it. So a general rule of thumb is that if you have one class that is more than 70%, so 70% no, 30% yes, you have imbalanced data. So what can we do about it? All right, so this data set, very imbalanced. Okay, options. One option is to do what is called undersample the majority class. So we take our data set and we could use the command sample to take the group. So let's take the part of the data set that is the no's, and instead of taking all of the no's, we take just some of the no's. So we're going to undersample. We're going to take a subset of the no's and we're going to then use it to create our classification model. And the idea is we're rebalancing the data by making there be less no's, so the ratio of no's to yeses is closer to each other. Okay. So we'll look at how to do that in just a second, but just to tell you there's another option. Another option is to oversample the minority class, in which case we need to create synthetic data where we create more yes rows to our data set. So the challenge with this, of course, is that you are having to create synthetic or fake data that is similar to the yeses in the data set, but you can't just duplicate the section of the data set that is the yeses, because if you just copy pasted your 100 responses that were the yes buys and you just made them happen twice, there's no variability in that data. So it doesn't really strengthen our model any by just duplicating that data. It's about having the variety within. The challenge, of course, is that it's not real data, it's synthetic. So you need a good way to create synthetic data that mimics the behavior in that minority class. And so now you're getting into general adversarial networks. So we're using AI to create the fake data and then training it. So basically, we're having two neural networks, one that creates the fake data, the other one that's trying to identify whether it's fake, to strengthen that data set. And so the computing power and the processing for this gets a lot more complicated. There is also a method called SMOTE. Just here, we just SMOTE, not smite. And so we're talking about SMOTE, we're talking about synthetic minority oversampling techniques. So it's another method, not quite the neural network version, to create that synthetic data. So there are approaches to oversample the minority class, but they do get more complicated. So we're going to focus in this video just on the undersampling approach. Okay, so how does this work? Well, let's go to our data set here. Okay. So what we have is that banking data set that you see here, and just like all our other videos, we import pandas and NumPy, we link it to our Google Drive, and we look at the data set. We use our test train split to split the data set, and in this case, let's look at age and balance to see if we can predict whether or not they buy those GICs. Just like in our last video we talked about, we stratify, we shuffle, and we're going to do about a 20% test. In this case, we are trying to predict buy, no buy, so we can do a generalized linear model, classification model. Check out the other videos for how that works. And here we're going to then import that logistic regression and accuracy score to see if we can create a model and how accurate it is. So we call the model, we fit the model, we predict. What you'll notice is that the model predicts all no's. So it's quite possible these variables are terrible, these variables are good, doesn't really matter. It is that the data contains so many no's that it just predicts no regardless. So what do we do about it? Well, notice that this accuracy of this model is still quite high, but it's just predicting that no one is actually buying. So our confusion matrix shows us the yes, no in terms of the actual labels and then our predicted labels. So what we could do is we could take our data set, our original data set, where in this case, our original data set is 4,000 no's and 521 yeses. That's what this length is showing us, is the number that of rows that have that attribute where the y variable is no. So what we want to do is use a command called sample, where we then take a subset of just the no's. So I've separated the no's and the yeses into two separate tables. We went from a single table, we've separated them out so that we have a no table and a yes table, and now we're going to sample, take a subset from the no table. Oops, let's not do that. That is going to be smaller. So then the question becomes how much smaller, right? So we are trying to undersample and rebalance the amount of no's versus yeses. And we were currently at 86% or so for no and the rest for yeses. 70%, 30% is considered to be imbalanced. So we can readjust. How do you do that? Well, what we do is we take a sample and you say how many. It's going to randomly pull from that table And the question is, how many do you want to pull? So if I have it this way, the length of the other table, we're going to end up with 50-50. Okay. Now, that may not be representative of what real life is like, so that might be overkill, and it might be a poorly fitting model depending on the correlation between your variables and what you're trying to predict. Is there really a relationship there? So you might be somewhere between equal in size. Maybe you're going to do so that this is a 25%, 75% adjustment if we do it 3 times, right? So then we have 3 times for this one and 1 for that. So you end up with 75, 25. So you can do an adjustment here. Ideally, you want it to be more representative of real life in terms of like what percentage of people actually do buy. If you don't have that information, then you're adjusting it. But remember that when you do this adjustment, you also might find, like we do here, so I think what I have here is just one-on-one. Notice that now I get a lot of yeses because I rebalanced it so half the data set is yeses and half the data set is nos. The accuracy is low, 50%. Coin toss, we might as well just toss a coin as to whether or not they're going to buy or not. So not super helpful. So even though we do this rebalancing, we need to recognize that we also need good variables. And if these variables are not helpful in predicting whether someone buys or not, doesn't matter how much you rebalance. Yes, you're going to get some people now in the yes category, but in this case, it's a 50-50 whether or not whether or not we predict correctly. It's a coin toss. So we want high accuracy, but we also want to detect the patterns in that minority class. Now, in this particular case, we've been using accuracy, which just looks at they predicted yes, was it yes? There is another method for assessing accuracy when you have imbalanced data, and that is what is called F1. So when we've been doing our classification models, we've been looking at precision. What percentage of those that were predicted true were actually true? Okay, so when we look at precision, it considers the impact of the false positives. We also looked at recall. What percentage of the actually true were predicted to be true? So it's looking at the impact of the false negatives. And so I'll just temporarily move my face here. This is the confusion matrix that we saw in color in this video. Now you can't see that, that you see here. That's color coded, looking at the true positives, the false positives, the true negatives, the false negatives. Okay. So we're looking at this relationship here. That's why we keep looking at that confusion matrix to see what is happening. We knew, just move my face back. We knew the original model was no good because this whole side was just zeros. Okay, and looking at the data, it just predicted everybody no. The new version that we have here has these yeses, which is great. Our confusion matrix now has numbers on both sides, but it has an accuracy that's only 51%. So another way to assess the model is to look at the F1 score. To find the F1 score, use sklearn.matrix and FK1 score, just like the accuracy is based on the test and the predicted. Now, notice in this particular code we're staring at, it's giving me errors. That's because if you want to use the F1 score, you can't have your labels be yes and no. You have to change your labels to 1 and 0. It is looking for 1 and 0 when it does that calculation. So it's an adjusted version of the accuracy that takes into consideration both precision and recall and that trade-off between. So to run this, make sure that your data labels are 0s and 1s. It won't calculate it with anything else. So when it comes to F1, the way that F1 works is that it takes 2 times your precision times your recall and divides by the precision plus the recall to look at the accuracy, but take into consideration that having a low precision and a high recall is problematic. Having a high recall, or whatever the opposite is, low precision, is just as problematic. So it's combining the two as it looks at your accuracy. So if we have imbalanced data, instead of just looking at the accuracy percentage, we want to look at F1, okay, which you can get from sklearn.matrix, import F1 score, test and predict, but make sure you have encoded your data so that your label is 0, 1 rather than like say yes, no, or words. Okay. To wrap up our discussion on prepping our data, the last thing to consider is building a pipeline. So we've been talking about extracting, transforming, and loading our data into our AI algorithm so that we can call the model, fit the model, and predict. So we can create pipelines that are data pipelines. For example, in other videos, we've looked at a cleaning function that took our text that we scraped from a PDF and got rid of a bunch of the weird symbols, like whenever you scrape text that has like returns and spaces in it, it turns it into weird symbols. So we would get rid of all of those. We'd get rid of the URLs and emails and things that don't have meaning. So creating a function where you keep applying the next thing to the previous piece. So you can see we're doing all of these to the text, and then just going through the next piece. This is a pipeline, a data pipeline where we are transforming the data. We also have videos where we look at, for example, how do we take a bunch of text documents and decide that this is one theme and this is another. In that case, we were doing a model pipeline. So here, with the code that you see here, we are going to have our truncated SVD, our single value decomposition, and then we have our k-means for our clustering. And so these are the two models we're going to specify. We first, of course, need to import those packages, but we call the model, and then we fit the model, and then we predict. So we have a pipeline here. There's actually a function called pipeline. And if you make a pipeline, it says, okay, I'm going to first apply this package. So it's going to apply the model, this model, and then the results, it will apply the k-means model to it. And so it takes the output and then applies the next piece. So it allows us then to apply multiple approaches in that model pipeline. So we specify the model, we fit the model, we predict, and we can use functions like pipeline to do multiple ones simultaneously. There are other pipelines we could create for deployment and for tuning. You could create a system, right, that is all encompassing, which has your data prep, your model, and your service, and so allowing then for you to update your model as new data comes in, fine tune it, deploy it, all within one system. So the idea of a pipeline is simply the fact that we are going to build a process where the data will flow through, whether we are extracting and transforming it, whether we are using it to build a model. And so it allows us to kind of automate that process. And that could be simply in the form of functions. That can also be in the form of creating pipelines using existing packages.